Okay, in our next installment of ecology, today we're focusing on populations. Remember, populations are the number of organisms of one specific species in an area. So we're not dealing with a community where it's all of the different species. We're only focusing on one species now. So a couple important vocabulary words that come with population. First off, just the definition. So a population is just the number of a single species in an ecological community. So one type. That's all we're concerned with. Population density. Now this is a measurement of how many are in a specific area. So you take the number of individuals, you divide it by the area, and that is your population density. So our practice problem, if we have a density of 200 deer in 10 square kilometers. So we would take 200 deer divided by 10 square kilometers, and that is simply going to end up being 20 deer per square kilometer. As you see with the map here to the right, you have population density from 2015, where we see the majority of people kind of in the world. Now with populations, we also have dispersion patterns. So how populations are distributed. You have clumped, basically uniform or nearly uniform, and random. Now clumped are going to be those that live together in groups. All your animals that live in herds. Nearly uniform, individuals that live at specific distances from one another. This could be a competition. A lot of birds will specifically build nests at specific intervals between other nests, just to make sure that there's not too much competition for resources. And then random's random, so it's spread in no particular pattern. So clumped, a herd of deer or a school of fish, that's going to be clumped. So we're going to see something like they're all kind of huddled in one general area. That's clumped. Nearly uniform is where they are spaced out in particular intervals, forming pretty much an equal pattern. And then random is simply no pattern whatsoever. So when we look at the pictures over here, our school of fish, that nice clump pattern. Penguins typically are uniformly spread out, kind of when they raise their young. And a random pattern, a lot of plants just simply sprout up here and there. There's no kind of rhyme or reason to where they end up. So, a couple scenarios here. Three-toed sloths have almost no competitors and few predators. So no competition, few predators, they're going to spread out. And there's going to be no rhyme or reason in terms of how close they need to be to each other since there's no competitors. So this is going to be a random pattern. There is no reason to be clumped together for protection, and there's no reason to be split apart from one another at certain distances because you're competing for the same resources. Fish. A lot of fish travel in schools for protection. So we would say fish exist in clumped dispersion patterns or distribution patterns. And penguins protecting their young, we see that right here, how they're kind of spread out evenly, kind of power in numbers and spreading things out. It's not necessarily a herd. There is space in between them, so each kind of look after their own. And we're going to call that uniform. Now, population dynamics. What causes populations to grow and shrink over time? Well, births are going to increase because for every new organism born, you are adding to the population size. Another thing to add to the size is immigration. New organisms joining the group. That is all going to add. On the other hand, shrinking. Well, when things die, you don't have as many in the group, or when things leave. Emigration. Now, when the births and immigration rates are greater than the deaths emigration rates, you see a population increase. When the deaths and emigration are greater than the births and immigration, you are going to see a population decrease. When you see these rates equal to one another, we would say the population is stable. Now, the final thing is simply looking at population growth. We have two types of growths. You have exponential and you have logistic. Now, exponential growth is increasing greatly over a period of time. There's plenty of resources, so there's not much competition. So what happens is it grows rapidly, very, very quickly. Now, exponential growth is going to be kind of best possible scenario. Logistic growth, this is going to be more reality. Where what happens with logistic growth is you have a period of slow growth, so you do see that exponential line right here with logistic. But then it starts to tailor off because now we're seeing a competition for resources because the environment can no longer support that increased population. Now, an environment has what's called a carrying capacity, and that is the max amount of individuals that environment can hold at any given time. Now, this is going to be different per species. You know, a forest might be able to sustain, 20 deer, but maybe it can sustain 40,000 beetles. So it really depends on the species in terms of their needs. But we see kind of more that S-shaped curve of logistic compared to that that J-shaped curve of exponential. So logistic, what this factors in is what we call limiting factors. What is limiting the size of the population to either be below or meet the carrying capacity? Now, if the habitat is damaged, the carrying capacity will decrease for everything. So logistic growth is a little bit more realistic. Exponential growth is if there were no limiting factors and everything had all unlimited resources, this is what would occur. So our carrying capacity the maximum number of individuals of a particular species that the environment can support. It can change. As we see over here, an unrestricted deer population growth may diminish the habitat's carrying capacity. It originally was right here. But with the habitat being destroyed, it now cannot sustain as big of a population. So the carrying capacity for deer actually decreased with the destruction of the habitat. But going back to logistic growth, we do have our limiting factors, which we kind of talked about a little bit already. What affects population size? A lack of space, climate, disease, predation, drought. A whole lot of things can affect population size. But we can group these on density dependent and density independent factors. Density dependent are affected by how many are in that area. Density independent does not matter how many are in the population whatsoever. It affects any population size equally. So what we're going to find is your density dependent factors. These are going to be more biotic factors, because since density is a variable, anything that is biotic is going to have an effect. So examples of this will be availability of food. If you have more organisms, you're going to have less food. Predation. We talked about the predator-prey relationship. More prey means more predators. Less prey, less predators. Disease. Disease can really wipe out large or small populations. Typically, larger populations might lead to greater chance of disease. Migration. And then probably most importantly, a big one, there's always competition. Now, density independent, these are going to be abiotic in nature, non-living, because the living factors, the community, the populations, will have zero effect on these limiting factors. So these are non-living in nature, and these are going to be an example of temperature. Doesn't matter big or small, temperature can affect the population. A natural disaster, a hurricane, doesn't really care if where it hits has a small or large population. And then just overall weather. So abiotic, density independent. It does not matter what the population is. Biotic, density dependent. It depends on the size of the population to really figure out how extreme that limiting factor is going to be. So the final thing today, just looking at this picture, predation, going with our predator-prey analysis. More predators is going to mean less prey. More prey means more predators. And then dealing with abiotic, drought. If there's not a lot of water, that's going to affect everything equally. So that's the big thing with density independent, is that it's going to affect large or small populations equally. Density dependent, large and small populations are not going to be affected equally. Right, that marks the end of ecology. So far we've covered, we talked about the biosphere, we hit different biomes, we talked about the cycling of ecosystems, the interactions of communities. Today was all about population dynamics. So if you have any questions, please ask. Thanks for watching.